we are going to discuss about batteries. Now, batteries work on electrochemical reactions, and we have two important cells to study. One is primary cell and the second is secondary cell, and we have examples also coming under primary cell and secondary cell. So let's first study about primary batteries or primary cells. Now, what do you mean by a primary cell? In primary batteries, the reaction occurs only once, and after use over a period of time, the battery becomes dead and cannot be reused again. That means we cannot charge the battery and use it again. That is primary batteries. Now, we have two examples to study under primary battery. The first example is Leclanché cell or dry cell. Now, when we study the examples for batteries, you have to study what is taken as anode, cathode, electrolyte. Now, the reaction at anode, reaction at cathode, and overall reactions. So, in Leclanché cell or dry cell, the anode is zinc and cathode is carbon rod surrounded by powdered MnO2 and carbon. And the electrolyte taken is a moist paste of ammonium chloride and zinc chloride. Now we know that this works like an electrochemical cell. So again we have at anode oxidation and cathode reduction. Now anode is zinc. So if you look at the reaction at anode, it is the oxidation of Zn2 plus Zn to Zn2 plus. Now the reaction at cathode. Cathode is carbon rod surrounded by powdered MnO2 and carbon. And at cathode we have MnO2 plus NH4 plus. This NH4 plus came from our electrolyte ammonium chloride. Plus one electron is gained. It changes into MnOOH. This is called manganese oxyhydroxide plus ammonia gas is produced. Now this ammonia produced will combine with Zn2 plus and we get a complex with formula ZnNH3 4 times 2 plus. So the ammonia produced will combine with Zn2 plus and we get a complex ion. Now the overall reaction for this is Zn plus 2MnO2 plus 2NH4 plus gives Zn2 plus 2MnOOH plus 2NH3, and this ammonia produced combines with Zn2 plus to form the complex. Now we know that the potential of a dry cell is 1.5 volt and dry cell is usually used in transistors, clocks, etc. Now the second type of primary cell is mercury cell or button cell, and mercury cell or button cell is usually used in hearing aids. It's used in hearing aids and watches. Now let's see what is the anode, cathode and the cell reactions. In mercury cell, the anode is zinc mercury amalgam and cathode is paste of mercuric oxide and carbon. Electrolyte is a paste of potassium hydroxide and zinc oxide. Now the reactions at anode is zinc amalgam plus 2OH minus. At anode, oxidation takes place. Gives zinc oxide plus water by losing 2 electrons. Now at cathode, mercuric oxide plus H2O plus 2 electron, we get liquid mercury plus 2 OH minus. And the overall reaction is zinc amalgam plus HgO. We know that this H2O, 2 electron gets cancelled. So 2OH minus and 2OH minus also gets cancelled. So overall reaction is zinc amalgam plus HgO gives zinc oxide plus mercury, liquid mercury. Now the cell potential of mercury cell is 1.35 volt and it remains constant during its life as the overall reaction does not involve any ions. So this is one of the advantage of mercury cell over dry cell. Okay, so since it does not involve any ions, its concentration cannot change during its lifetime. Now, the next type of battery is secondary batteries. Now, what are secondary batteries? A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. A good secondary cell can undergo a large number of discharging and charging cycles. And the most important example for a secondary cell is lead storage battery. Which is used in automobiles and inverters. So, example 4, secondary cell is lead storage battery. Now, let's see what is anode, cathode and the electrolyte and the overall reactions taking place in lead storage battery. The anode used in lead storage battery is lead and cathode is a grid of lead packed with PbO2. Electrolyte is 38% sulfuric acid. Now, let's see the reactions at anode and cathode when the cell is in use. That means the cell reactions during its discharging process. Let's see the reactions at anode and cathode. At anode, we have oxidation. So, Pb, lead plus sulfate ion. The sulfate ion came from our electrolyte sulfuric acid. We get lead sulfate and 2 electrons are lost. Now, at cathode, we have cathode is grid of lead packed with PbO2. So, we have reduction of PbO2. PbO2 plus SO4 minus plus 4H plus. This comes from sulfuric acid plus 2 electron. We get PbSO4 plus 2H2O. Now, let's see the overall reaction. In the overall reaction, you can see on the reactant side, we have Pb plus PbO2 plus 2H2SO4. That is, here we have 4H plus and here we have 2SO4 2 minus. So, we can write it as 2H2SO4. Now, 2 electrons and 2 electron gets cancelled. Now, on product side, we have 2PbSO4 plus 2H2O. So, this is the overall reaction. That is, we get lead sulfate and water as the product in the overall reaction during the discharging of lead storage battery. Now, let's see what happens to the reaction when the cell is charged. During charging, what happens? During recharging, what happens to the reactions? We can see that all the reactions will get reversed. So, the overall reaction will be the reverse of this reaction. So, the cell reaction during charging is 2PbSO4 plus 2H2O gives Pb plus PbO2 plus 2H2SO4, which is the reverse of the overall reaction during its discharge. Same way, we can see all the anode and cathode reactions also gets reversed, which means the anode reaction will be the reverse of this. Means now this will change. During charging, anode will become cathode and the reaction at cathode is reduction. So, the reduction will be the reverse of this. That is PbSO4 plus 2 electron giving Pb plus SO4 2 minus. Now, during charging, recharging at cathode, this cathode will become anode. And anode we have oxidation reaction. So, that will be the reverse of this reaction. That is PbSO4 plus 2H2O will get oxidized to PbO2 plus SO4 2 minus plus 4H plus 2 electron. So, during recharging the anode and cathode changes, the reactions also changes. Okay, so these are the reactions taking place during discharging and recharging of a lead storage battery. Now, the next example for a secondary cell is nickel-cadmium cell. Nickel-cadmium cell, anode is cadmium, cathode is metal grid containing nickel 4 oxide and electrolyte is moist KOH solution. Now, the overall reaction, we have no reactions at anode, cathode in the textbook. So, we have only the overall reaction. And the overall reaction is cadmium plus nickel hydroxide will give cadmium oxide plus NiOH twice plus H2O. So, two examples for secondary cell. One is lead storage battery and the second is nickel cadmium cell. Now, the next type of cell is Fuel cells. Now what are fuel cells? Fuel cells are galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy. They are called fuel cells. So in fuel cells, the chemical energy produced during combustion of fuels like hydrogen, methane, methanol is converted into electrical energy. And we have got to study one example for a fuel cell, that is hydrogen oxygen fuel cell. And this hydrogen oxygen fuel cell, the final product that we get in the hydrogen oxygen fuel cell is water. And this fuel cell was used for providing electrical power in Apollo space program. The water vapors produced during this reaction were condensed and added to the drinking water supply for the astronauts. Now let us see what is anode, cathode and the reactions taking place in hydrogen oxygen fuel cell. Now in hydrogen oxygen fuel cell, the anode is carbon, cathode is also carbon electrode, and the electrolyte is aqueous sodium hydroxide. Now at anode, hydrogen gas gets oxidized to water, H2, 2H2 plus 4OH minus gives 4H2O plus 4 electron, and at cathode oxygen gas gets reduced, O2 gets reduced to 4OH minus, and you can see the overall reaction is formation of liquid water by the combination of hydrogen gas and oxygen gas. You can see in the reaction this 2H2 plus O2 will give 4OH minus gets cancelled, and 4H2O this side and 2H2O, so it gives 2H2O. So this is the overall reaction taking place in fuel cell, that is formation of water. Now let us see the advantages of fuel cells over other cells. There are three advantages. The first advantage is the cell can run continuously as long as the reactants are supplied, because it is the hydrogen and oxygen gas that we are providing. So the cell can work for a long time. The second advantage is fuel cells produce electricity with an efficiency of about 70% compared to other cells. And the last advantage is these cells are pollution free. Fuel cells are pollution free because the final product that we get is water. So pollution free. These are the three advantages of fuel cells over other cells. Now the last topic is corrosion. Corrosion. What do you mean by corrosion? Corrosion slowly coats the surface of metallic objects with oxides or other salts of the metal. Rusting of iron, tarnishing of silver, or formation of green coating on copper, bronze are examples for corrosion. Now here we have to study the reactions involved in the rusting of iron. So this corrosion reactions are for the rusting of iron. Now the reactions taking place during rusting of iron involves electrochemical reactions. Now you know what is a rust? Rust is hydrated ferric oxide, that is Fe2O3.XH2O. Now since it's an electrochemical reaction, we know that there will be an anode, cathode, overall reaction possible in this. So let's see how a rust is formed. Now on the particular any part of an object made of iron, what happens is oxidation, a particular point on that iron object, oxidation takes place. So oxidation of iron takes place, and that part of that object will act as anode. So we can see the reaction at anode. At anode we have iron getting oxidized to Fe2 plus by losing 4 electrons. Now the electrons released here will move through the object and it will reach some other spot where the reduction of oxygen takes place. Reduction. So that spot behaves as cathode, and the reduction reaction of oxygen is O2 plus 4H plus 4 electron giving 2H2O. And you can see the reduction of oxygen takes place in presence of H plus ion. Now this H plus ion is formed by the dissolution of water present in the atmosphere. This H plus is formed from the dissolution of carbon dioxide present in the atmosphere in water. So you know that H2O plus CO2, we get carbonic acid H2CO3, from which we get this H plus ion. So the reduction of oxygen takes place in presence of H plus ion, and this is the reduction equation. So we got our anode and cathode on the ion object. Now the overall reaction is 2Fe plus O2 plus 4H plus gives 2Fe2 plus 2H2O. That is, Fe2 plus is called ferrous ion. This is ferrous ion. Now what happens to this ferrous ion? Ferrous ion will get oxidized by atmospheric oxygen to form ferric ion. This is ferric oxide Fe2O3, and here ion is in +3 oxidation state. So Fe2 plus 2H2O plus O2. Ferrous gets oxidized by atmospheric oxygen to ferric oxide plus 4H plus. Now the ferric oxide formed will absorb water from the atmosphere, and we get Fe2O3.XH2O, which is called hydrated ferric oxide, and this is our rust. So rust is chemically Fe2O3.XH2O, and it is called hydrated ferric oxide. So this is the reactions taking place during rusting of iron. Now let's see how to prevent corrosion. One method is by painting the surface. Now the second method is by electroplating the surface iron metal with more active metals like zinc, magnesium, etc. And that method of coating the iron with zinc metal is known as galvanization. So these are the two methods by which we can prevent corrosion. So thank you.